I'm going to be talking a bit about the board game Go and the state of the art in computer Go AI. So first, a brief introduction to Go. Go is a board game which was invented in ancient China, and it's still very popular in the East Asia. It's an abstract two-player board game with perfect information, and it has really, really simple rules. So black and white take turns placing one stone each. Black goes first, and for each stone that's on the board, you have 4 orthogonally adjacent points, and those are called the stone's liberties. And as you can see in the leftmost diagram, a stone with no liberties, meaning those liberties have been taken up by the opposing player's stones, that stone in the middle is captured and is removed from the board. Groups of orthogonally adjacent stones of the same color share their liberties. So in the rightmost example, you can see that the 2 black stones in the middle will have 6 liberties in total. And in order to capture them, all 6 must be occupied with white stones. The game ends when the 2 players pass one after another. And then they count up who controls the most territory, meaning basically the points on the board where the opponent couldn't possibly play without getting captured. So the player controlling the most territory wins. And that's it. So here's a position from a very, very famous game, which was played back in 1846 between a 17-year-old Honimbo Shusaku and a Inoue Genan, who was one of the most famous players of that era. And move 127 in this game is considered to be one of the most famous moves in Go history, and it is this move. So what does this move do? Well, if you have a look at the group of stones down here, you can see that they're being threatened by white stones. So by placing a stone here, you're actually reinforcing them and helping them to live. Black has quite a strong group of stones up here, and that's also being reinforced by the stone that's placed here. And furthermore, black is looking to attack to the left because at the moment, white has quite a strong influence, but this was the stone that started the kind of invasion into the left of the board. And so 17-year-old Honimbo ended up winning this game by 2 points of territory because he managed to keep these 2 groups alive and start the attack because of this one famous move. So this gives an idea of how Go is really rich in strategy despite its simple rules. And it also gives an idea as to why it's so hard for computers to figure out Go as a game. This is quite an abstract move, which you might not be able to clearly see the effects of until, say, 30 moves in the future. So computers aren't very good at seeing stuff like this. For every game-playing AI, for a 2-player zero-sum game, we can represent it as some kind of game tree, where we have nodes, which represent positions in the game, and edges, which take us to new positions after basically playing a move. So in this way, we build up a tree. A game-playing AI typically has 2 tasks. Firstly, it has to be able to evaluate, meaning you take a position, and you statically look at it and say, this is likely winning for white, or this is pretty much a draw. And you do that by using domain-specific heuristics. So for example, in chess, you might count up the value of white pieces and the value of black pieces and use the difference between those as a very rough evaluation. There's also search, which is the most important part of a game-playing AI, which is where you expand the game tree as far as you can see in the future and choose the most likely moves that each player is going to take. In that way, you can basically decide whether the first move that you're going to make as the current player is going to lead to a beneficial outcome in the future or not. And this is typically based on minimax, which means that the players alternate in trying to maximize and minimize a value because they have two opposing aims. The most important thing about search is to try and reduce the branching factor, which is to ignore bits of the game tree which are useless to us because they're obviously bad moves. So typically, we use something like an alpha-beta search to do that. So this is the only slide about, well, a game that's not Go in the entire presentation. It's about chess. And I put this in because I wanted to contrast what's been happening in the chess AI world with Go. So in chess, we're now at the stage where you can grab an open source engine online, and it will be able to run on your own PC and beat the greatest grandmaster alive right now. So chess has gone a long way. And most of the improvements have been through search advancements, the biggest being principal variation search. All of these techniques kind of come together to reduce the effective branching factor to less than 2 for most positions, which is why a chess engine can now look 30, 40, or more plies into the future. So this didn't really pan out for Go. None of these improvements translated into the Go world. Why is this? So first of all, a traditional search has to basically give up the search somewhere down the line. So when the tree bottoms out and we don't have time to go any further, we have to take the resulting position and evaluate it without searching. So we have to look at the position and immediately say, oh, that's obviously winning for white. That's not too hard to do for chess, because if, say, white is down the queen, then obviously it's a winning position for black. For Go, it's much harder because it's all about territory, not about, say, the pieces on the board. You can't just count the pieces. I guess the corresponding concept for Go would be groups of stones which are alive or dead. So alive stones means you can't kill them no matter how hard you try. And dead stones are, even if you try to save them, they'll eventually get captured. But Krasmeru, back in 1999, proved that even this problem, which is the most basic kind of concept in Go, is NP hard to evaluate. More problems with search in Go is it has a huge branching factor because the game board gets more and more complicated as the game goes on, and you can play almost everywhere on the board. Almost every move is legal. And it also has a much bigger board than chess. All of these factors add up to traditional search not working for Go. So this is why the Go engine world was kind of stagnant for at least 15 years up until 2006. In 2006, the state of the art was an engine which could scrape a draw with a strong beginner, say, but no better than that. But something magical happened in 2006, and Go engines have been skyrocketing in strength since then. So I'll be talking about the improvements that, the advancements that were discovered in 2006 in this presentation. Okay, so the entire kind of new idea that was implemented in Go engines hinges on this concept of Monte Carlo. So what is Monte Carlo? Monte Carlo is just a term that refers to algorithms which are randomized and work with simulations. So in order to find a result, what you do is you do lots and lots of simulations, take some kind of statistical average of the result, and then use that as an estimate of the answer to the problem that you were trying to solve. In our case, we want to solve whether a move, an action, is good or bad. So we can take a position, which results, and then we can use Monte Carlo simulation, which simply means play random games starting from that same position every time. And so, for example, here, we start with this board, and we just put down random moves. And we carry on until the game is over. We just look at who won, whether black won or white won. and then we accumulate all of those results, and that gives a statistical estimation of how good this position is for black. So this immediately gives rise to our first search algorithm. Well, it's not really a search algorithm, but it gives us an action which is deemed good to play from a root position. So this is the flat Monte Carlo algorithm. You have a position at the root, and you want to find out which of, say, 3 actions is best. So you pick a child node from these red nodes at random, and then you perform a playout, which is just one of these random simulations. Then you backpropagate the results. And then eventually you will store up some statistics for each of these 3 actions picked at random. So eventually you will build up a good idea of which move is good and which move is bad. We'll just carry on doing this until we've exceeded our computational budget, we get bored. So it works pretty well. I mean, if you think about it, we don't have to use an evaluation function. We're always playing games out till the very end, so we don't have to worry about that. That's probably our biggest advantage. But it's also anytime, meaning we can always query what's the best that we've got so far. It's also embarrassingly parallel. We can just kick off multiple simulations. They never interact with each other, so it just scales up. On the other hand, it's actually not that good. It's symmetric. So if we have lots of actions, and quite a few of them are obviously bad, like we've done 100 simulations, and 99 of them have led to a loss for us, it will still carry on treating it uniformly. And as time goes by, it will not learn to ignore those actions. So that's a disadvantage for us. It's also not consistent. When we leave it running for a very long time, it doesn't necessarily converge to the correct game theoretic best move. And we'll see how to deal with that later. But first, let's look at the symmetric problem. What we're doing here is we have a problem in selection. So if we go back to the algorithm, we basically have 3 steps. There's the selection step, where we pick a child at random. We play out, and then we backpropagate the results back up. The problem here is selection, because we're just choosing uniformly at random. But actually, we want to take into account the results that we get from performing the selections. So there's a mathematical model for this. It's called the multi-armed bandit problem. The name just stems from the fact that we have lots of slot machines, which are called one-armed bandits, because they have an arm that you pull, and when you pull them, they rob you of all your money. So this is the multi-armed bandit problem. We have K slot machines, or K arms, as I'll call them. And at the beginning, we don't know anything about them, except that they will give us either no reward or exactly 1 reward. And the mean reward is, we write the mean reward of an arm K as mu of K. There exists some arm K star, which has the highest expected reward, mu of K star. But we don't know which one it is. So we have to find out as we play. Our objective is, after playing n times, so we pull arm K1, K2, up to Kn, we want to minimize the regret. And regret is kind of the idea of, what did I lose out by not having picked the optimal arm every single time? So it's the sum of mu of K star take away the mean of the arm that we actually did pick at time t, right? So our objective is to minimize this. And there are lots of different kind of strategies for solving this problem. And we've already come up with one, the uniform strategy. Ignore the outcome and just pull random arms. But that's not very good, because we want to, once we get an idea of the best arm, we want to exploit it by pulling it more to get less regret and more reward. So that leads us to our second strategy, the greedy strategy. We have an idea, the empirical mean, which is the kind of average so far that we know about a machine. We'll write that as mu hat of k at time t. And so we have an idea of what the mean of each machine is. Why don't we just pull the one which has highest mean every time? Then surely we'll minimize our regret. So formally, at time t, we pick k of t to be the I, which minimizes mu hat of I at time t, which maximizes even. So we pick the one with highest empirical mean. But there is a problem with this. So imagine we have a two-armed bandit set up here. One of them has mean a third, and the other has mean 2/3. We give them both a pull first, just to bootstrap the strategy, just to give it a defined empirical mean. And it turns out that the first outcome for A happens to give us a reward, but the outcome for B gives us no reward. So then the greedy strategy is going to go with A for the rest of eternity, because the average for A, the empirical mean, will never drop down to 0. So the problem here is, although we're trying to exploit the best arm every time, our strategy fails because we don't explore the other options. We could be exploiting a pretty good arm, which is not the actual optimum arm. So we get a glimpse here of the exploitation and exploration kind of trade-off. So in 2002, a paper written by Auer et al. Outlines the upper confidence bound strategy. And the idea behind this is we want to, not only do we keep track of the empirical mean, we want to keep track of how much information we have about each arm relative to the other arms. So if we have an arm which we haven't pulled very much relative to the others, then we probably want to give it some more pulls just to make sure that we haven't actually let slip a better arm. So what we do here is we define a confidence interval in which we believe the actual mean, the distribution mean, lies. And then we pick the arm which has the highest upper confidence bound at every time. So you can see here how I've defined the upper confidence bound. It's just the empirical mean plus the size of the confidence interval. This term is also known as the exploration term because it encourages us to explore other arms. And you'll notice that it depends on t, which is the time, or the number of arms we've pulled so far, and also big T, which is the number of times we've played arm K up to this point. So as time goes by, the exploration term will increase. So we'll eventually get around to playing this arm again, even if it's not optimal, just to explore. But the more we pull this arm, the smaller this confidence interval will get, because we now know more and more about it, and we're more certain about what the actual mean is. So formally, we just define this bound, and then we pick the arm I such that the upper confidence bound is maximized. Cool. I have a demo. It's a very bad demo. Excuse the badness. This is a graph. I have 4 armed bandits, which are the lines, basically. And this is a graph with the y-axis being reward. So the black line at the bottom represents 0, and the black line at the top represents a 1. I've preset the true means of each of the arms set to the positions of the black dots that you can see. So for example, arm 1 is our true, the arm to the left is our true optimum arm. So we would like to pull that the most. So this is what the red lines represent the confidence bounds. And currently they're all infinite because we have no idea about any of them. So what the algorithm goes and does is it pulls the 4 arms 4 times just to get an idea. You can see that the empirical means of arms 1, 2, and 4 are now 1 because we got a reward from them. And we got nothing from arm 0. Arm 3, we got 0 from arm 3. So now what it does is it looks at the upper confidence bounds, and it picks the one which is highest. In this case, it could pick from any of 1, 2, and 4. It goes ahead and pulls arm 1 again, and it got a 1 again. And you'll see that the confidence bound for 1 shrunk because it knows more about it now, whereas the confidence bounds for all the other 3s increased. So now we're not going to explore 1 again, even though it gave us another 1. We're going to explore arms 2 and 4. So if I run another iteration, it will pull arm 2. And you'll see that we actually got a 0. So the empirical mean dropped to a half now. And the confidence interval also shrunk. So now it's arm 4's turn, and we pull arm 4. And the same happened for that. And so if we keep on going, you'll see that although at the beginning we're pulling fairly uniformly, you can see already that we're starting to pull arm 1 a lot more. It's not really helped by the fact that we got all 1s from arm 1 so far, which is quite a freak accident. But if we run 100 iterations, you'll see that they start to converge to the true means. But the thing that you'll notice is that arm 1 is getting pulled many, many more times than arm 2 and arm 3 and arm 4. And if I keep this going, they actually, the non-optimal arms actually get pulled a logarithmic amount of times as time goes by. OK? So we've started to minimize our regret by doing this. That's good. OK. OK, so actually, we're going to prove that UCB is optimal. I mentioned that UCB allows cumulative regret to grow on the order of log t, so logarithmically as time goes by. But a classic paper by Lai and Robbins back in 1985 actually proved that there is no multi-arm bandit strategy which has better than logarithmic growth for a very large class of reward distributions. So we're going to prove that UCB does have this logarithmic cumulative regret. OK, so let's get started. Suppose that we're at time t, and we happen to pick a suboptimal arm k. That must mean that the upper confidence bound for k is currently bigger than the upper confidence bound for the true optimum arm, k star. So we have b k of t is greater than b k star of t. And we can just expand out the definitions of the upper confidence bounds. OK, so now we make an observation which is quite important. You'll see that during the demo, the confidence intervals never actually excluded the true means, right? So they were actually, the confidence intervals did contain the true mean. So we're saying that with high probability, this is actually the case. In particular, we only care about 2 of these inequalities. The first being for the suboptimal arm, mu of k, the true mean of the suboptimal arm is greater than the lower confidence bound that we've created for that. And for the optimal arm, the true mean, sorry, wrong way around. Let's go back. The true mean of the suboptimal arm is greater than the lower confidence bound, and the true mean of the optimal arm is lower than the upper confidence bound that we've constructed for it. So this happens with very high probability. And if those 2 really do hold, what we can do is a simple rearrangement of these 2, and then plugging it into this inequality to get a new inequality, which only involves the true means rather than the empirical means. And it's very easy to show this on paper, so I won't go through the details. But rearranging this inequality again, we get an expression for the number of times that we pulled arm k. And so this bounds the number of times that we pull a suboptimal arm according to something that is logarithmic with time and is multiplied by a constant which depends on how far the true means deviate. So using this, we can actually just bound the cumulative regret. It's very straightforward. We take the definition of cumulative regret, which is the sum of the regrets over all the times, all the n times that we pull the arm. But we observe that actually we can also express the cumulative regret with regard to the number of times that we pulled each arm. So instead of summing the regret at every pull, we sum the regrets for each arm multiplied by the amount of times that we pull that arm. So it's just rearranging the summation. So we get this equation, we get this expression, and then we just substitute our inequality that we obtained for the number of times that we pull any suboptimal arm k. And for summing over all the k's that are not the optimal arm, we get this. So you can see that as n, the number of arm pulls increases, the cumulative regret is bounded by a constant specific to our bandit setup, multiplied by log of n. Now, this actually only holds when we assume that these two conditions at the top are true, which empirically they are. But it's possible to complete this proof by using the Chernoff-Hofting bound, which is a bound in statistics. And all that does is it adds a small constant to this bound. So the expected regret remains bounded by remains bounded on the order of log n. So that's pretty cool. We've got a very good selection strategy now, but there's still a weakness with flat Monte Carlo. And the issue now is with the second disadvantage that I mentioned earlier. We've solved the symmetry disadvantage, but now we have the issue of inconsistency. So if we leave this algorithm running forever, it won't converge necessarily to the game theoretic true value. And this is because the playout policy, the policy that we choose when we're playing out a game till the very end, is weak. Flat Monte Carlo falls prey to, for example, if you have a look at this game tree, it's player A's turn to move, and he can either move to the left or the right nodes. If he moves to the left, player B can only have one choice, and then it's player A's turn to move again. And then there's a choice which leads to a win for player A. So player A can actually force a win from the root position. This is a win. On the other hand, if player A chooses to go to the right, it's player B's turn to choose out of a move which causes player A to win, or a move which causes player B to win. So obviously B can force a win. So if A goes to the right, A loses. On the other hand, if you give this to the flat Monte Carlo algorithm, because it only looks at the top three nodes, it chooses uniformly from, or it chooses according to some selection strategy, either the left or the right node, and then it does playouts. For each playout that happens from the left node, there's a 20% possibility of A winning. So that statistic is 1 in 5. Playouts starting from the right, because they're randomly played, there's a 50% chance of A winning. So to flat Monte Carlo, it looks like the right node is the right one to go with. So it plays the wrong move. Even if you left this running forever, it would converge to 1/5 on the left and 1/2 on the right, which is wrong. So the problem here is that there's no opponent model. We're playing completely randomly. We don't care about the fact that player B is trying to maximize their value, and player A is trying to minimize player B's value, and vice versa. So this is why flat Monte Carlo isn't a true search algorithm. It doesn't take this into account. It doesn't take the minimax principle into account. So the idea is we need to fix this. And we already have a good selection strategy. So could we somehow use the history of selections that we've made in the past to incrementally build up a search tree that we can go through to find the optimum? And so this is the basis for Monte Carlo Tree Search, which was introduced by Rémi Coulomb in 2006. And the paper that introduced it basically started the entire Go AI revolution. It's a very simple tweak to flat Monte Carlo. There's one extra step that's been added. So it now goes selection, expansion, then the simulation, then backpropagation. And what it does now is it works on trees. So the selection stage now recursively uses a bandit algorithm to choose a child, then that child chooses a child. Eventually, you'll get to a node which doesn't have a full set of children, which means that we haven't visited it enough to have explored every single action from it yet. So in this example, this child only has this node only has one child, and there's another action which we haven't explored yet. So then, when we encounter that, we add a new node, a new child node to that, in the step called expansion. And that's uniformly chosen out of all the possible actions that you could take from this original node. OK, and then from there, we just do the simulation as before, and then backpropagation as before, except all of the nodes along the path back up to the root have their statistics updated. So in a way, you can think of this as still kind of flat Monte Carlo, except we're extending the policy. We're extending the playout policy. So at first, it's the tree that's guiding the policy. We're going through the game tree to guide the search. And only in the second part, we use the default policy of just playing out randomly until we get a result at the end. So this actually, if you think about it, it maintains all the advantages. It's still anytime. It's still mostly parallelizable. The parallel threads have to make sure they're not stepping on each other's parts of the tree. But it's still parallelizable. And but the big thing is it overcomes the disadvantages of flat Monte Carlo. And those are that it's now asymmetric. Because the selection strategy can now pick more often the promising child nodes, and every time we pick a node, we're going to grow out a new node from that area of the tree. So if we select kind of one area of the tree much more than another, it will grow deeper and deeper, and we will search more into more promising areas. So for example, in the graph to the right, where we have one set of actions which actually leads to a very promising result, which is why they search deeper, just to make sure that that is indeed the case. And if you're careful, Monte Carlo Tree Search is also consistent. This depends on the selection strategy for picking the child nodes. And I shall prove that when you apply the UCB, upper confidence bound selection strategy, it actually results in an algorithm that is consistent. So when you combine Monte Carlo Tree Search with the UCB selection strategy, you get the UCT algorithm. And it was proven to be a consistent strategy by Coxis and Sepesvari also in 2006. And the proof roughly goes like this. So you'll notice that in UCB, although we exploit the most optimal arm a lot, actually every arm, if we left it running forever, every arm would get pulled infinitely often. If you think about it, this is because if we left an arm unpulled for a very long time, its upper confidence bound would grow without bound, because the logarithm diverges to infinity. So eventually, it will exceed the upper confidence bounds of all the other arms. And so we're going to have to pull it. So each arm is pulled infinitely often. When we apply this as the selection strategy, that also means that each node is visited infinitely often. And that means that every single part of the search tree will eventually get expanded, which means that eventually, we'll have the entire search space for Go stored up as the search tree. There won't be any bits missing. The next thing to notice is that as time goes on, the UCB strategy will cause the node's values to tend to the values of its optimal children, which means that if there's a good move, it will eventually get its value propagated up and up, further and further up the tree. And because we've built the entire tree, we can guarantee this is the true game theoretic optimal value. And eventually, this will get up to the root node, and then that will contain the true value, and then we're done. It's consistent. So this is all well and good, but in 2007, Gelly and Silver came up with a refinement which, once again, added a huge amount of strength to Go engines. And this is interesting because up to now, I've been talking about Go AIs, but I haven't actually included any kind of references to Go. The algorithm so far is pretty game agnostic. You can apply it to many different games. But this is a very good heuristic, which is especially applicable to Go. And the heuristic is called AMAF, all moves as first. So the observation is, when you have a Go game, and you're searching a particular position, and say 4 moves in the future, you find playing at point h5 is a very good idea because it led to a win. It's probably very likely that playing at h5 right now from the current position, rather than 4 plays in the future, from the current position, h5 would also be a good move. Because Go is additive, you always add to the board. There's no, once you put a stone down, it never gets shuffled around. So playing at h5 is likely also a good idea right now. So the way that we can apply this to the Monte Carlo Tree Search is when we're doing the back propagation step, we've got a playout, and say it led to a win. Then we assume that every single action that happened from our side in that playout could be played from our current position, which we're back propagating the statistics back into, and they would also lead to a win because they're also good moves. So we take every single action in the future and play them as if they were played from the current position, and then we update the statistics for them for a win, and vice versa for a draw. Which means that for every one playout that happens, we might, say, update 10 actions statistics for every node. So this gives us a very, very quick estimate of the value of each position, of each action. And this is a good thing because remember when we were discussing UCB, one of the things that we mentioned was at the beginning when it has nothing to work with, it pulls the arms pretty much at random, uniformly. Once it has something to work with, it will start exploiting the optimum. But when we apply the all moves as first heuristic, for every playout that happens, we update a lot of statistics. So we're giving the UCB strategy a lot to work with right from the get-go. So it kind of kickstarts the process, if you like. And so this is what RAVE, Rapid Action Value Estimate, tries to do. It records the statistics that we get from Monte Carlo simulation, the playouts. It also records separately for each node the statistics that accumulate from the all moves as first heuristic. And then at the beginning, when we don't have many simulations, we take the statistics from AMAF seriously, and we use them to be fed into the bandit algorithm, the bandit selection algorithm. Once we have some more meaningful data from the simulations, we will start to interpolate and use the Monte Carlo simulation results instead, because they're going to be more accurate. AMAF is only a rough kind of indicator. So using this refinement, Go engines improved many, many times in strength. So, yep. OK. So now we're kind of at the frontiers of current research, which is quite exciting. So right now what's going on is people are still trying to figure out the best way to integrate Go-related heuristics into the search algorithm, because Monte Carlo Tree Search in itself doesn't contain many kind of heuristics itself. So the current research has been going into biasing selection. So what that basically means is before you do a search, when you encounter a child, when you encounter a node, when you want to select a child, we artificially bias, we artificially increase the values of some of the children because some kind of static evaluation tells us that that is a likely child for us to win. So that is a good move. So we can use traditional methods such as looking up patterns in databases or looking up openings in opening databases. We can also use heuristics in life and death. And recently, there have been papers investigating the use of neural networks to analyze how good a position potentially is and what the next move could be. But the way that they integrate into the Monte Carlo Tree Search is not during playouts, but during selection, when we increase the value of a potential child node because we think it's probably a good idea to search it before the others. There's also the problem when we bias, where it's actually very hard to maintain consistency. Once we bias a search, the fact that we're introducing heuristics might mean that it fails in some cases. And if it fails so hard that over time it doesn't actually converge to the true value anymore, then we've lost consistency, which was one of the main advantages of pure UCT. So there have been research into the necessary conditions for maintaining consistency, and Berthier et al. Wrote a paper on this in 2010. The other area of active research is in alternative bandit strategies. So you'll notice that I mentioned that UCB is optimal with regard to cumulative regret. There's also a concept of simple regret, which is ignore what happened when we were actually experimenting and pulling arms. All we care about is, at the end, can you tell me which one is the optimal arm? So it's basically like, go away, pull them for however many turns. I don't care how many, what happens during those turns, as long as you come back and tell me which one you think is optimal. So it doesn't care about the history, it only cares about the final result. And so that's the simple regret. And a strategy which optimizes simple regret is SHOT, which is, the simple regret bandit strategy is called sequential halving. When applied to Monte Carlo Tree Search, it's called SHOT. And that can be used as an alternative to UCT or as a hybrid kind of policy with UCT. The interesting thing about bandit strategies is there was actually a proof that any bandit strategy which is optimal with regard to cumulative regret cannot be optimal with regard to simple regret and vice versa. So it's quite surprising. And so we need empirical kind of testing to see which approach is right for Go. So what's Monte Carlo Tree Search now being used for? Because originally, when Coulomb introduced this in 2006, it was for the purpose of computer Go. And it's doing remarkably at that. Before, it was only kind of taking on strong beginners. And now, in 2013, I believe, there was a kind of exhibition match between the strongest Go engine at the time, Crazy Stone, written by Coulomb. And Crazy Stone won against a professional 9-dan player with a 4-stone handicap, meaning that Crazy Stone was allowed to play 4 stones on the board before the game started. So there's still progress to be made. Go engines can't beat in a fair matchup yet, can't beat the Go champion, say, but we're getting there. We have successfully applied Monte Carlo Tree Search to Hex, which is another game where you try to join up 2 sides of a hexagon, I believe. And Monte Carlo Tree Search is now world champion at that. There's also been experiments applying it to non-deterministic games, like backgammon, poker, and even real-time games. Apparently someone did one which beat Mrs. Pac-Man, so there's that. Multi-arm bandit theory is also very interesting because as a mathematical model, it's very flexible. So you can apply it to, for example, clinical trials, where you want to save as many patients as possible, but at the same time, you want to determine which of the drugs is optimal, so you can use it from then onwards. Similarly, for ad placement on, say, web pages, you want to experiment with visitors. You want to try out different ad placements, but at the same time, you want to gain as much revenue during the experiment as possible. There's also the problem of investment and resource allocation, where you have a fixed amount of, say, money, and a certain number of projects which could give you some reward in the future, but you don't know which ones. So you have to kind of decide which ones to give money to. So yeah, that's the end of my talk. I'm happy to take questions.